So that means I will be having 3 boost parameters. For example, boost along x direction, boost along y direction, and boost along z direction. And how many rotations are possible? 3. So that means how many total parameters this transformation consists of? 6 parameters. So that means a general Lorentz transformation in 4 dimensions comprises of how many parameters? 6 parameters. Okay, 3 parameters corresponding to boosts and 3 parameters corresponding to rotations. Okay, now the point is that if you see Lorentz transformation, okay, so if I am having 6 parameters, how many generators I can define? 6 generators. So we have a rotation group, only 3 parameters. How many generators? 3 generators. So if we are having 6 parameters here, that means I can define 6 generators corresponding to the Lorentz group. Okay. So let's first define a Lorentz group. What a Lorentz group means. Okay. So these are the Lorentz transformation, and we know under this kind of construction, the interval remains invariant. This ds square, it is an invariant quantity. Okay, under this kind of transformation. Okay, so what is the condition of the invariance? This we have already figured out. Okay. So this is the condition under which this invariant remains invariant. So in other words, you can say lambda inverse lambda is equal to identity. Clear? So this okay, so this is the condition under which this remains invariant. The way we are having the condition, this length square, okay, remains invariant under the rotation group. What is the condition? R transpose R is equal to identity. The same thing is here. Okay? Clear? So now let me redefine this in this fashion. Okay, so you are having a matrix G here, is it? G is a matrix and G is a matrix. Let me define it as a G, this capital G. Okay? And I will write this as lambda transpose G and lambda. So this is equal to G. Clear? In a symbolic way, without any kind of indices. You can see it. Okay, so you can write this thing, this object like. Okay, so let me write lambda mu nu G mu rho lambda rho sigma is equal to G nu sigma. Clear? So this way, one will be the transpose of the other. Clear? So that's why I have put it this way. So that means I am having a set of matrices now. Lambdas are now the set of matrices. Clear? We satisfy this very condition, and this set of matrices form a group under matrix multiplication. Clear? So now, okay, so let me put it this way. If I am given a set of matrices, okay, let's assume 4 by 4 matrices, okay, that satisfy this very condition. Clear? This very equation, and we say they form a group under matrix multiplication. The operation is simple matrix multiplication. Clear? And we call such group as a Lorentz group. Okay, so let's show it. Okay, so what is at hand? So I am having this. Okay, so I am having the set of matrices lambda. Clear? And what is the condition they satisfy? Lambda transpose G, lambda is equal to G. Clear? So this is the set of matrices at hand. Clear? And I am saying this set of matrices form a group under matrix multiplication. So this is a group under what is the operation here? Simple matrix multiplication. Clear? Okay, so now let's show it. So what is the first condition? Closure. Okay, so let's calculate the closure. Whether this is closed or not. So what I will do, let me take lambda 1 and lambda 2, okay, they belong to this, sorry, there is a G, so let me write it L, okay, let's write it L, clear? So they belong to L, so to this very set. What does that mean? So it means this lambda 1 G transpose, lambda 1 is equal to G, and lambda 2 G lambda 2 is equal to G. Clear? So because they said if they belong to this very set, they satisfy this condition. Clear? Okay? So now let's take the product, this kind of product. So therefore I am having this lambda 1, lambda 2 product and take its transpose. So that means lambda 1 and lambda 2 I am taking an checking whether this element exists in that set or not. Clear? So then I will write this way, lambda 1, lambda 2. So let's check it. So it will be simply equal to lambda 2 transpose, because when you take the transpose of the two matrices, it will be in the inverse fashion, okay, in the reverse order, okay, G lambda 1 and lambda 2. Clear? Got it? Okay, so now what this object is by definition? Lambda 2 inverse, what this object is by definition? G, okay, then lambda 2. So what this object is? G. So that means this product, since this product, okay, transpose G and the product. So it gives you the G back. That means the same condition, clear? So it means this product, so lambda 1, lambda 2 belongs to where? This here. Clear? So it means it's closed under multiplication, or it is closed under group operation. So we have figured out the closure, and second thing you need to figure out the associativity. So check this lambda 1, lambda 2, lambda 3. It is same as lambda 1, lambda 2 and lambda 3. So this will be the assignment. So just check it. Just check this closure, this associativity follows from the closure relation. Clear? Got it? Now what is the another object we need to figure out? Whether there exists identity or not. Clear? So let's write, let I be the identity. Okay? This be the identity. Okay? So I know, so if this is an identity, so identity transpose G, identity, what it is equal to? G. So that means this identity exists in L, because it satisfies the same condition. So what you need to know, a matrix, its transpose G and the same matrix is equal to G. So it means I exists where? In the group, in this L. Clear? So it means identity is there. So which implies I belongs to. Okay, what is the third point? We need to figure out whether there is inverse or not. Okay, first let's check the condition of the invertibility. Lambdas are the matrices, is it? So when its inverse is possible? When determinant of the matrix is non-zero. If it is zero, then we have the problem with the invertibility. Clear? Okay, so now let's check. So we are having, so let's check determinant of this lambda transpose G, lambda, so that's equal to determinant of G. Clear? So what I am taking, so you take an element lambda, and that satisfies this lambda transpose G, lambda is equal to G, and take its determinant. Clear? Okay? So now what is the determinant of G? G is the metric tensor. What are its elements? 1, minus 1, minus 1, minus 1. Okay, what is the determinant? Product of the diagonal terms, that's minus 1. Okay, so this is minus 1. What this will be here? So it is determinant of lambda transpose, determinant of G, and determinant of lambda. Clear? Samajh aawa? Everybody is following it? Okay. Now determinant of lambda transpose and determinant of lambda, they are same. So I can write this as determinant of G is minus 1. Okay, so this object is equal to minus 1. This will cancel with this thing. I will be having simply determinant of lambda square. Okay, so that's equal to 1. So what it means? Determinant of lambda is equal to plus minus 1, which is not equal to 0. What it means? Lambda. Okay, so inverse exists. Clear? And we need to check whether this inverse is in the group or not. We need to check whether this inverse exists in this set or not. Now let's check it. Okay. So can you tell me how to do that? Huh? Can you tell me? Okay. So let's write. So I am having this very condition. Lambda transpose G, lambda that's equal to what? G. Okay? Clear? So now let's multiply on left. Okay? Let me multiply on left by lambda inverse. Okay? And its transpose. Like this thing. And on right, G, like this thing. So on left I am multiplying this thing. And on right I am simply multiplying by lambda inverse. Clear? Got it? So what I am doing, so you take this thing, on left you multiply by what? Lambda inverse transpose. Okay, on right you multiply by what? Simply lambda inverse. Okay, so what it means? So it is simply lambda inverse transpose G lambda inverse. Clear? Right hand side. So on left you are multiplying lambda inverse transpose, then you are having G, and right you are multiplying lambda inverse. So this object I can write this way. Lambda inverse transpose. Can I write it? Transpose of the two things, it will be lambda inverse transpose, lambda transpose G, and lambda inverse. So what that is? Lambda inverse transpose G lambda inverse. Clear? So what this is equal to lambda inverse? It's identity. This also equal to, so this is identity transpose, this is identity. So what it means? I am having G is equal to lambda inverse transpose G lambda inverse. Clear? So that means lambda inverse satisfies the same condition as lambda. Clear? So what you are having? An element, its transpose G, the element. Clear? Is equal to G. What is the element here? Lambda inverse transpose G lambda inverse. So it satisfies the same condition. Clear? So what does it mean? It belongs to the group. So that means the inverse exists within this set. So what we have proved? So obviously inverse. What we have proved? So the set of matrices which follow this kind of condition, lambda transpose G lambda is equal to G, form a group, and we call this group as a Lorentz group. In general, you can show. Okay, in general, lambda 1, lambda 2 is not equal to lambda 2, lambda 1 in general. Okay, so that means it's a non-abelian group. Clear? So everybody has got the idea of the Lorentz group? Huh? Any question? Everybody has got the idea of the Lorentz group, what the Lorentz group means? Okay, here what we have done, we have taken this lambda. Huh? So this lambda we have taken, it's a 4 by 4 matrix, and it comprises of two things, boosts as well as rotations. Now if I take boosts separately, they do not form a group. Lorentz boosts themselves do not form a group. Lorentz transformation is, the total Lorentz transformation forms a group, but Lorentz boosts, that means if you are making a particle to move with a velocity along a certain direction, we call those as boosters, and those transformations do not form a group. Clear? Now let's take these boosters. So now let's take a boost along x direction. Okay. So along x direction, let's take it. So how we write it? Just tell me. So if I have to define this x0 as ct, x1 is equal to x, x2 is equal to y, and these things we have done a couple of times. I am just repeating. So this is the Lorentz boost matrix. So you are having x0 prime, x1 prime, x2 prime, and x3 prime. They transform this way. So you also define here gamma is equal to 1 divided by root of 1 minus beta square, and beta is equal to v by c. Okay, so this is simply the usual Lorentz transformation along x direction. Okay, so what you know already. Clear? Huh? So this is the usual transformation. Okay. So let's write this. Okay, so let's parameterize. Since we are having this very condition, gamma square minus beta square gamma square equal to 1. So it is rewriting the same equation. Huh? Now let's look. What is gamma square? 1 divided by, so it will be simply 1 minus beta square minus beta square gamma square. Okay, so it will be simply 1. I am rewriting the identity. Clear? Is it true? So it is equal to 1. So because of this very condition, okay, because these appear gamma here and beta gamma here, what I will do, I will re-parameterize gamma in terms of some angle. Clear? And that angle is sometimes known as rapidity, okay, or the boost parameter. Okay, so what is the parameter here? No, what is the parameter if I write it in this way? It is simply the velocity. So this is the velocity along x direction because I am choosing the particle moving along x direction. Clear? So the parameter here is simply what? Velocity, because I can change only the velocity. Okay? Clear? So what I will do, I will use this kind of objective using that very condition. Gamma is equal to cos hyperbolic phi and beta gamma is equal to sine hyperbolic phi. So that means I am making a rotation in the complex plane. So the usual, when we think of the rotations, we do it in the real plane through an angle theta, is it? We are having those cosine phi's and sine phi's, is it? So we can think this Lorentz transformation as the rotation in the complex, or the rotation through a complex angle. Huh? Okay. So now let's try then what this will be. So it will be cosine of phi here. Okay. So let me write this as a matrix B. So let's call this as a B. Okay, boost matrix along x direction. So therefore I can write the boost matrix along x direction. How? Just tell me. Cosine hyperbolic phi minus sine hyperbolic phi 0 0 minus sine hyperbolic phi cosine hyperbolic phi 0 0 0 0 1 0 1 0 0 0. Clear? So this is the boost matrix along which direction? X direction. Clear? What is the parameter here now? What I can change? To show you what I can change? Phi. Phi is the angle which I can change. Clear? Huh? Is that true? Okay. Now I have rewritten this. Okay. So I have changed my parameter from velocity to phi. Clear? Actually, phi you can write in terms of the velocity. Can you write it? So now let's divide the two. Sine hyperbolic phi divided by cosine. So what that will be? Tan hyperbolic phi. And that will be actually your velocity. Clear? So your beta is simply equal to what? Tan hyperbolic phi. What is this beta? B by C. So that means you are writing velocity in terms of the phi. Whether you write in terms of velocity or you write in terms of phi, it's okay. Clear? Eh? There is no problem. Huh? Why I am writing it in the phi? Because I have taken rotation in terms of the angles. Eh? So now I will take boosts in terms of the angles. Okay? So now if I have defined this boost, so then I should be able to define a generator corresponding to this boost. Okay, when the generators are possible? When we define the generators of a group? Now look here. So we have just constructed a group, what we call Lorentz group, is it? And this Lorentz group has how many parameters? 6 parameters. 3 corresponding to boosts and 3 corresponding to rotations. So that means our Lorentz group comprises of how many objects? 6 objects. 3 boosts and 3 rotations. Clear? So we are in 4-dimensional space-time. Clear? Now I have constructed a boost matrix. So this is a matrix corresponding to a boost. And this boost is along x direction. Is it? Now if I have constructed a boost, what I should construct now? A generator. The way we have defined the generator for the rotation group, Okay, let's say the rotation through z direction, x-axis or y-axis, and we have defined these generators. Similarly, how we can define the generators corresponding to all the 6 objects? Okay, all the 6 these transformations. Clear? Huh? Okay, so now how we define the generator? Let's call that generator as kx. How we define it? 1 by I partial bx by partial, what is the parameter? Phi, and phi you put equal to 0. Clear? Is this how we define the generator? And we define generator for a continuous group. Is Lorentz group a continuous group? Let's tell me, is Lorentz group a continuous group? Okay. What does that mean? I can construct a finite element from the infinitesimal ones, is it? So if you are having, let's say, finite boost along x direction, you can construct what? It from the infinitesimal ones. First infinitesimal, then infinitesimal, and so on, up to you reach the finite one, is it? You can continuously go from the smaller element to the larger element. Clear? Samajh aaya? So in that way, it's a continuous kind of transformation. Okay. So what this will be equal to? Minus I when you say. So okay, so it will be 0, minus 1, 0, 0, 0, 0, 0. So this is the boost generator along for the Lorentz transformation along x direction. Clear? Everybody followed it? Huh? Now if I, instead of constructing a boost along x direction, let me construct a boost along y direction. That means I am making a Lorentz transformation along y direction. What will remain unchanged? X and z. Clear? Samajh aaya? So x and z will remain unchanged, only the y coordinate will change. Y and this time coordinate, they will change. So that means where these ones will shift. So it will go here. So samajh aaya? So let me write now. Similarly, we can construct a boost generator along y direction. Now kya humne? So it is 0, 0, minus 1, 0, 0, minus 1, 0, and put rest things what? Clear? And what is now kz? What is kz? Just tell me. I 0, 0, 0, minus 1, 0, 0, minus 1, 0, 0, like this. Clear? So these are three generators corresponding to boosters. Okay. Now when let's assume our transformations are only these 3 transformations, and check whether it's a group or not. What I need to know? First thing I need to know whether it is closed or not. If the group elements are closed, it means generators will give me the closed algebra. Is it? What does that mean? Okay. Take an analogy from the rotation group. You are having the elements of the group are closed. Is it? So let's say R1 multiplied by R2 is equal to R3, and R3 belongs to the group. Is it? So in other words, it means, let's take the generator along for the time being along x direction and generator along y direction. What you will get? Lx, a commutator between Lx and Ly, or Jx and Jy commutator. What it yields me? Jz. I time is Jz, is it? So Jz belongs to the group, is it? It is a generator corresponding to the rotation along rotation about z axis. Clear? So that means if you multiply two generators, you get a third generator, and that belongs to the some element of the group. Clear? So in other words, the algebra is closed. Clear? Now let's assume our transformations are only defined by these 3 generators. Since they define only the boosters, and let's check whether these boosters form a group or whether they are closed or not. If they are closed, that means our boost elements form a group. Clear? If they are not closed, that means they do not form a group. Samajh aaya? So this is a very important condition. If you are having elements of a group form a elements of a set form a group under a given operation, then their generators must be closed. Clear? So they should form a closed Lie algebra, what we call that commutator. Okay. So now let's check it. So let's take kx multiplication, kx ky minus ky kz. Sorry, kx. Is it a commutator between kx ky? So now let's check it. So what it will give me? Just multiply. Just multiply. No? Multiply. Let's multiply kx and ky. So what is the first okay? So it will be 0. No. First element is 0. So let's write. And minus I, it is minus. Okay? Then what you will get? So let's take. So first element is 0. Second element is 0. Then 0. Then 0. So now let's take the another element. 0. Now 0 and 1. Is it? 0. No. You are having minus 1 and you are having minus 1 here. Clear? Look here. So this row and this column 0. This row and this column 0. This row and this column. So the first will multiply. It is 1. Clear? Got it? So then 0. What then next? You are having all zeros. 0, 0, 0, 0. So we have missed actually one something. Okay, so it's like this. Then minus ky kx in the other way. So it's minus and minus, it will be plus. Now let's check it. What it will be? 0, first element, then 0, then 0, 0. Clear? So you are having 0, 0, 0, 0 because all are zeros. Then you are having what?
0, 1, 1.
Okay, 0, 1, 0, 0, 0, 0, 0, 0. So now let's add the 2. So what you are having? When you say? So it is minus times. So let's take minus out. Okay, so it will be something. Okay, 0, 0, 0, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 0. Now tell me, is this any boost generator? Is this any boost generator? So it should have been kx, ky. Okay, if they formed a group, it should give me a kz, but it does not. It's actually, if you see, it's simply equal to minus I jz. It gives actually the rotation along z direction. It may, okay, look here. So you are making a boost along x direction, then boost along, then return. So it will give you actually the rotational effect instead of the translational motion. Clear? So it is simply the rotation about what? Z axis. That is why it will give you minus I times jz. Okay? Oh, samajh aaya? You got my point. So this is very important. Two boosts, although they do not commute, but they give you a rotational effect. And this is actually the reason. Okay, this is actually the mechanism behind Thomas precision. Okay, have you done it in the atomic physics? Thomas precision. Okay, forget that. Clear? So now you have seen, since the generators do not, the algebra of the generators is not closed, so it means it does not form a group. So boost generators do not form a group. So now let me write, okay, so everybody has written it. So now let me write the angular momentum operators or these rotation of generators in the four-dimensional notation. Okay, so now let's write these rotation generators. Okay, so the first thing is, let's say Jx. Clear? So let's write it in the four-dimensional form. Since they do not involve any time, clear? So there is no time axis. That means you can put 0 along the time axis. So these are actually, if you are having any element along this kind of thing, you are having boost, is it? Since rotation do not involve a boost, so you are having only the elements. What is the Jx? So it is something, let me write in the four-dimensional form. I, okay, 0, 0, 0. You have to write that Jx 3 by 3 matrix here. 0, 0, 1, 0, minus 1, 0. And then you are having the Jy minus I times, okay, 0, 0, 0, 0. No, I mean this minus 1. Then you are having 0, 1, 0, 0, 0. And then you are having this Jz equal to minus I 0, 0. Okay. Clear? So now how many generators are there? 6 generators. Now these generators, these 6 generators specify you the Lorentz transformation, a general Lorentz transformation. Clear? Okay. Now let's take, so let me write the algebra between the two. You now you have shown, okay, we have just seen this, let's say kx ky minus ky kx is equal to some jz. Okay, so what was there? 1 and minus 1, is it? Is that true? Huh? So 1 and minus 1 we had. Huh? So, and we have put a minus side outside. Clear? So, samajh aao? Okay, so now let me write. Everybody has written it? Okay. So now let me write the algebra carefully. Okay. So this is the home assignment for you people, and check element wise. So this is the algebra. So this ki, kj, where I and j go from x, y, z, this is equal to minus I epsilon I jk. Okay. So that means two boosts yield you a rotation. Clear? And it is, so it is not closed under this algebra. Clear? Okay. So now if I am taking, since I am having 6 generators, so I need to look at the algebra of all the 6 generators. Clear? Whether the generators, whether the algebra is closed or not. Okay, we have shown elements of Lorentz transformation form a group. So that means the algebra should be closed. Clear? Okay, so let me tell you what exactly that means. Okay, jk, so ji, kj, so these are only the 3 possible commutators. So it is kk. Okay, now look here. All these, okay, so taking into account all these 3 commutators, so the algebra is closed. Clear? Now look here. So you get from 2 boosts, you get actually a rotation, is it? And the rotation belongs to the Lorentz group, is it? Is that true? And 2 rotations give a third rotation, and that is there, eh? Because what are the generators? What is the set of the generators? Kx, ky, and kz, jx, jy, jz. Is it? So that means, so you are having a rotation and a boost. Is it what it gives me? A boost. So that boost belongs to the set. Is it? So that means taking into account all the 6 generators form a closed algebra. Clear? Samajh aaya? Okay. Now this is all about these things. Now let's check how these act on the stiffeners. Okay, so now let's construct the Lorentz transformation rule for the stiffeners. How stiffeners transform under a given Lorentz transformation. This is in general for a 4-dimensional vector. Okay, let's say if you are having a 4 vector, and how Lorentz transformation acts on, you just apply lambda acting on that vector, you will get what? You will get a given kind of rule, is it? But how it acts on a stiffener? Now let's take to the 2-dimensional space. Okay, or a stiffener space, whether it's a 2-dimensional space or it's a 4-dimensional space. So what kind of spacing? But we will consider a stiffener space, or we will consider how Lorentz transformation acts on the spin half particles. Let's say you are having an angular momentum half, and how the Lorentz transformation affected these half angular momentum objects. Clear? Got it? Okay. So for that matter, what I can, so there is actually a theory which describe the mathematical description which describes a group in one setting and the other settings, which gives you the relation between the two groups from one setting to the another setting. We call that as a representation theory. Okay, a representation of the groups. Like we have done, we have seen the O3 acts in the three-dimensional space, and SU2 we have done what? That means we have represented actually O3 kind of transformation in two-dimensional space. Is it? Similarly, if I am having, let's say the Lorentz group, okay, how it acts in the two-dimensional space. So that means what is a representation group that will act as a Lorentz group. So suppose what is the representation group of O3? It's SU2, is it? So that's why we call them, these are the isomorphic to each other. So now let's reduce Lorentz group let's reduce the Lorentz group to a space, to a simpler space. Clear? How it will act on these kind of objects. Okay, so okay, you don't need to consider these, mathematical ideas, but we'll go through the physical way. Okay, so let me construct it for that matter. Okay, so I'm having two types of generators here. Is it? Boost generators and rotation generators. What I will do, I will construct a new form of generators, from these boost and rotation generators. Let me define a generator A is equal to half of J plus IK, okay, and some another generator. So these are the two possibilities I can construct. Clear? So I have constructed two generators, is it? So and new generators out of these generators. And let's check what the kind of generator A is and what kind of generator. Okay, I have constructed A and B from rotations and boosters. Clear? And let's check what they give, what they yield. Is it? Samajh? Okay? So for that matter, let's construct first. When you construct a generator, check its Lie algebra. Check the commutator, right? Okay, so let's check first. So let's take this AI and AG. Clear? Let's check this commutator. Okay, so what is the commutator? So it is 1 by 4. Okay, shall I take half or not? Okay, half. Okay, so it will be something Ji plus I Ki, and then you are having Jj plus I Kj. Clear? So now let's write it. It is 1 by 4. So what is the commutator between Ji and Jj? Okay, so let me write in detailed form. Ji Jj, then you are having minus this Ki Kj, then you are having plus I, okay, Ji, then Kj, okay, then you are having minus, okay, plus I Ki Jj. Clear? So these are the four commutators I can construct. Now let's write this Jij. What is Jij? Okay. So here they are there. So it's I epsilon I Jk Jk. Clear? Then minus, what is Ki Kj? Minus and minus, that's plus I epsilon I Jk Jk. Clear? Now tell me what is Ji Kj? I times, so I is here, I and I is minus. So it's epsilon I Jk, then Kk. Clear? Then what's Ki Kj? It's minus, it will be plus epsilon I Jk. So it will be something like this, in epsilon Jik Kk. Clear? So you write it in this way because I need to keep track of the indices. You write it as minus times Jj. Clear? So what is this Ji Ki? I epsilon, so it will be J here, I here. Clear? Got it? Huh? Oh, wait. So this minus, okay, look here. I and I is minus, is it? Okay. So that way we will make this with plus. So now when you interchange the two, so it will be minus epsilon I j k. So it will be minus then here. Huh? So now let's add. So let's take I out. So these are 2. So it will be only half. So what you will get? Epsilon I j k you take out from every y, and you take I as well out. So what you will get? J k plus I k k. So what this is? What this is? J plus I k is A. So it is I epsilon I j k a k. Clear? So that means this is closed. The generators what I have constructed, what it is? It's a closed object. Samajh? It's itself closed. Okay. Clear? Samajh? Okay. Now if I okay. So now let's similarly check this bi. So bi bj. Can you check it? It will be also what? Closed. Okay. So this will be assignment. I will check it tomorrow. So then you check ai bj. This commutator is equal to 0. What I have done? What I have done? Anybody? We have actually we have constructed 2 generators, is it? So they are itself closed. Okay? So that means where from I have constructed? Huh? Where? From rotation and boosts, is it? So that means I have constructed from the generators of the larger group, the Lorentz group, is it? And I have constructed actually 2 groups here. Because when I am saying the generators of a, let's say you are having the set of generators, they are closed. What does that mean? The elements corresponding to those generators form a group, is it? So look here, think of the rotation group. You are having a rotation group here, its generators are closed, is it? So they give a closed D algebra. What does it mean? It itself forms a group. Samajh? And here the generators are not closed in case of boosts. That means it does not form a group itself. Clear? Now what I have constructed? I have constructed actually 2 types of generators which are closed under Lie algebra. Clear? And what kind of Lie algebra is? We call it as an SU2 Lie algebra. So if AI AJ is equal to like this thing. Samajh? So what we have done? We have started from a Lorentz group, and we have actually decomposed this Lorentz group into 2 groups. Because this set will form itself a group, this will form itself a... Okay, so this is very important thing. This AI and BJ, they commute, is it? So that means these are 2 distinct. If they were not commuting, it means they are not distinct. So Samajh? That means there will be the overlap of the elements between the 2 groups. Clear? So these are 2 distinct groups. Everybody followed it? Everybody followed it. So what I have done, okay? Now anybody having questions, just tell me. Huh? Okay. So okay, so what I have shown, yes, okay, so let me tell you, you have started from a larger group, Kx, Ky, Kz, let me write this way, Jx, Jy, Jz. So this is your Lorentz group, clear? So these are your Lorentz generators. And what you had done, you had decomposed it into 2 types of this Ax, Ay and Az, okay? So let me put a tensor here. So forget about this very notation. That means these are 2 distinct things. bx, by, and bz. Clear? Is this so? That means this Lorentz group is reducible to two groups. You have reduced. If that commutator was not equal to 0, let's say ai bj is not equal to 0. That means I can't say I have decomposed, I have reduced Lorentz group to two groups. Clear? Got my point? समझ आया? Okay. So what kind of group is this and what kind of group is this? So this is it because the algebra is an SU2 algebra. Okay, simply I mean the commutator. Okay. So that means this forms an SU2. This also forms an SU2. Okay. समझ आया? We have actually shown from rotation and both the generators of the SU2 and rotation group follow the same algebra, is it? So that's an SU2 algebra, clear? So that means this is what? It's an SU2, this is also what? SU2, okay, two distinct. So in other words, this Lorentz group, when it acts in a Sipner space, it acts like as an SU2 and SU2. समझ आओ? Clear? So it gives you the definition of what a Sippenhaft particle means. A Sippenhaft particle is simply a particle which transforms under Lorentz transformation as an SU2. Okay? Clear? So this is the definition of a Sippenhaft. Huh? Okay? You all understand what I have said? Huh? Okay. So in a moment you will see actually. So you started from a four-dimensional space, is it? Now you have decomposed it into SU2 is in a two-dimensional space and another SU2 is also in a two-dimensional space. Clear? Is that true? Okay, so you can label, let's say, since SU2 is essentially an angular momentum. Is that true? SU2 is an angular momentum because we have in the last case we have shown SU2 is simply an angular momentum algebra. Clear? So that means the states, the quantum states you can think, or the state vectors you can imagine. So you can label them with the angular momentum quantum number. Clear? Okay, so let's say if you have to describe the spin of the electron, how you describe it? By assigning the angular momentum half to the wave function. Clear? Now if you are having J is the angular momentum of the particle, how you describe this particle? Just labeling the angular momentum to that particle. Okay, now look here. Suppose if you are having Sippenhaft particle, okay, Sippenhaft of an electron. So how you describe your wave function? So okay, so you describe your wave function as the special component, okay, special component multiplied by spin component, is it? So we will take only spin component. What is the state vector corresponding to the spin component? So it will be, you will take half, okay, and the projection like this thing. You are having S and SZ. Clear? Is it true? So what S represents? Angular momentum. Angular momentum of half. What is SZ? Projection. Clear? So that means when you write in terms of the, okay, you can always assign a state to this very particle by giving a quantum number defined by the angular momentum. Clear? So that means if I am having a state vector here on which acts, so let's say it acts on some signal zeta 1 and zeta 2, last time we have seen, and let's say it acts on a signal eta 1 and eta 2. So these are two signals. So I can assign an angular momentum quantum number here. So that means this acts on a well-defined state defined by the angular momentum. Let's write that angular momentum to be J, and let's write the angular momentum here by J prime. समझ आवा? Huh? So that means the generators A will act on a state which is assigned a quantum number J, that's an angular momentum quantum number, and the generators B will act on a state that is defined by an angular momentum quantum number J prime. Clear? So that means the state, okay, so the complete state will be represented by this J and J prime, which will transform under a larger this Lorentz group. Clear? So समझ. So that means the state that is defined by this J and J prime will transform under Lorentz group as simply SU2 tensor SU2. SU2 SU2. Clear? So one SU2 will act on the first one, another will act on the second one. Clear? Okay. So let's take special cases, then you can understand what exactly it is. Okay, so this is, okay, so I can say this is the irreducible, okay, so there is a technical term here, we call this as an irreducible representation of the Lorentz group without parity. I will take parity in the next lecture. So if we don't consider the parity, so this is the irreducible representation. Irreducible means I cannot reduce it further. Okay, so let's give the simple examples. What is reducible and irreducible means. I will give a matrix. Let's say I am giving you a 3 by 3 matrix. Okay, so 3 by 3 matrix. All the entries are filled. Okay.
Just you want to add why should they?
Which class? So class important. Okay. So I am giving you a 3 by 3 matrix. All the entries are full, and I am asking you to diagonalize it. Okay, get the diagonal elements. What you will get? You will make some transformation and it will be a diagonal form. Let's say all entries are 0 and you are having, let's say, A, B, C. These are the diagonal terms. So that means I have reduced this matrix to a diagonal form. Is it? Okay. So although these are crude ways to understand the irreducibility, there are proper definitions. These are crude ways. You should understand it. I can say this is an irreducible represent because I cannot further make transformation. Let's assume there does not exist any other transformation which will further reduce it to some another form. Is it? Then I can say this is an irreducible representation of the previous matrix, that matrix. Clear? Now if it is not possible to bring it to the diagonal form, let's say if it is possible to bring, let's say if it is a larger group, larger matrix n cross n, let's say if it is possible to reduce to this kind of thing. So you are having one element 1 by 1, then let's say 2 by 2, let's say then 3 by 3 and so on. Okay, then up to let's say 1 by 1. So what it is? It's a block diagonal form. Clear? Such that the pieces of these you cannot decompose them further. I can say this matrix forms an irreducible representation of what? This matrix, original matrix. Clear? That means I am not able to decompose it further by any kind of transformation. Clear? Everybody clear? Now here what I have done, let's say you are having these matrices. What I have done? I have decomposed them into the new set of the matrices which I cannot further decompose. Clear? That's why we call this as an irreducible. So that means Lorentz group is reducible to SU2, SU2. In other words, I can say this is an irreducible representation of the Lorentz group. Clear? Now if I consider the parity, then this is not the irreducible. Okay? So without parity it is okay. So we will take parity then in the tomorrow's lecture, the next lecture. Okay? Okay, so let's take the special cases. Okay, so let me take these two states, J0 and 0J. So what does it mean? I am having, look here, I am having two signals, is it? Is that SU2 will act on one stiffener and SU2 will on the other stiffener, is it? So are these two stiffeners? Okay, while you are having the angular momentum state of the first stiffener specified by J and another is 0. And here the first is 0, another is J. What does it mean? Now let's write. So this will imply, so you are having A is equal to half of J plus IK, clear? and B is equal to half of J minus IK. So now look here, in the first case B is equal to 0, is it? So Samasha, what does it mean? So J, let's say for the jth element for this object, it will be simply I, K, J. Okay, so let me write, it will act as the jth element. So here B is equal to 0. So in this case, what you are having? Jj, it is minus Ik, because what that is? A is equal to 0. So in this case, A is equal to 0 because so you are having 0 angular momentum. Clear? So here B is having 0 angular momentum. So these are the J vectors. Okay, so sorry, the generators in terms of these case. Clear? So now let's take the specific. So let's take the type 1. So type 1. So let me take this J is equal to half. That means your half spin angular momentum. Clear? Samajh aa? So what I take? J is equal to half simply. So that means what is our stiffener? So our stiffener is, so it implies we are having this is the stiffener. Half and 0. Clear? Samajh aa? Okay. So what will be therefore the J half? So let me write the J half. Okay. So what it is? Anybody? It is K, is it? But what is that? What is the generator? What is the angular momentum generator acting on the spin half particle? It is sigma, Pauli spin matrix. Is it? What is the generator acting on the spin half particle? SU2 generator क्या है? Sigma by 2. Is it? So you are having sigma by 2 here. Huh? Clear? What will be there for K half? Minus I sigma by 2. Teacher? Clear? So now look here. So what this is? This is an angular momentum. And this transforms as an SU2. And what J is? J is actually the angular momentum generator. Clear? And what is the angular momentum generator acting on angular momentum generator in SU2? That's simply sigma by 2, Pauli spin matrix. Clear? And from that I have constructed what? The boost generator. What that is? Minus I sigma by 2. Clear? So now let's. So how much is time?
10, 50, 10, 40, 10, 50.
Okay. So let's take. Okay. So let me take. Let's denote this stiffener by. Okay. So let me write. Let zeta denote this stiffener. So how many transformations are there? Angular momentum as well as boost, is it? So there will be two types of parameters specifying these transforms. Clear? So let's take. Okay. So if theta and phi, let's write. So let's take theta as angular momentum parameter and phi as boost parameter. Now tell me how then this stiffener will transform. Can anybody tell me? Okay, listen carefully. What I am taking, instead of taking that half and 0, I am calling that as zeta as a stiffener. Clear? So look at the yesterday's lecture. So what we have done in the yesterday. So let's say you are having zeta, is it? Zeta will go as zeta prime is equal to u zeta. Is that true? Okay, u is an element of an SU2. Clear? So what is that element? E raised power I theta sigma. Is it true? Divided by 2 sigma. Is this how this transforms under SU2? Clear? So what you have to do, you multiply generator by the parameter. Clear? So how many parameters are here? 2 parameters. Clear? So that because we are having 2 types of generators here. So therefore under this Lorentz transformation, the zeta will go as zeta prime is equal to e raised power I. Okay, now tell me. So what is the angular moment? Okay, so it will be sigma by 2 dot with theta, is it? Clear? And then plus I minus I sigma by, okay, so let me write it for you people first. So it is e raised for I j half, okay, dots theta, clear? Then plus I k half, because there are two generators phi acting on theta. So this is how this sigma will transform under SU2, and this comprises of two types of generators, one for rotation, another for a boost. Clear? Because we are considering a larger group than the rotation group itself. Okay? So what that is equal to? What is J half? J half is equal to sigma by 2. So it will be sigma by 2 dot theta. It is through an arbitrary angle. That's why I am put theta is here. It contains a unit vector and theta, and will give you the direction. Okay, what is K half? Minus I, is it? So minus I and plus I is 1. Okay, so it will be simply sigma by 2 dot of zeta. Now first contains I, another does not contain I. Clear? So this is very important thing. So that means I can write it as e raised for I sigma by 2 dot of theta minus I. So this is how this type of Sepner transform is under SU2. Clear? That means our spin half particle under Lorentz transformation transforms in this way. So samajh aawa? Clear? So this is one type of Sepner. So let's define this m zeta. So we are having this zeta prime goes as, let's say, where m is equal to, it's not clear? So we have got one set of matrices M. We'll see in a moment their interpretation. Clear? So samajh aawa? Now let's take. So I am taking the type 1 Sepner. You are having this is the spin half particle. So samajh aawa? Spin half particle under Lorentz transformation transforms in that way. You will be having another type of spin half particle as well. Clear? 0 and half. Clear? So samajh aawa? So now tell me, what is the total dimension? If I take half and half, what will be the total dimensionality? You will be having one Sepner and another Sepner. That means two Sepners. So you are having two types of Sepners. So you will see actually in a moment what they correspond to. Okay. So now let me take another type. Okay, type 2 Sepners. Let's take. Let's take type 2. Okay, so here I will define type 2 Sepner is 0J. Clear? Samajh aawa? So 0J is and I will take this J is equal to half. So what that means? What is our type 2 Sepner? 0 and half. Clear? Samajh aawa? Any problem? Huh? Actually I am you will see actually probably in the tomorrow's lecture. So you will see actually what in Dirac equation we are having 4 Sepner, is it? Is that true? You will get actually the foundation for why the 4 Sepner has to be there. Why not only the 2 Sepner? So you will get. You should pay attention what I am doing. Okay, now tell me what is the J half here. So which implies, now tell me what is J half in this case. Minus sigma by 2. And what will be K half? It will be simply the opposite to that. I sigma by 2. Clear? Kisha? Na, Kathy. Plus should why not minus? Nala, so this is angular momentum. 7.5 particle are. So what will be the generator? Simply sigma by 2, not with a minus sign. Only K will change because in second case J is equal to minus I times K. K will be simply I times J. That's why there will be plus sign in K. So only the K generator will change. Clear? समझ आओ? So let's define these signals by eta. Okay? So let's call these signals are defined by eta, and eta will go as eta prime as, now tell me e raised power I, J generator, sigma by 2, so through an angle theta. Okay? So let me write theta and phi. So this is the angular momentum and this is boost. Okay? Then you are having plus I, and then you are having I sigma by 2 dot of phi acting on eta. So what that is equal to? E raised power I sigma by 2 dot of theta plus I. So let's call this as n eta, and n is equal to E raised power I sigma by 2. So now you are having two types of matrices, okay, two sets of matrices m and n, which affect, now look here, in n you are having plus I, okay, so you are having that theta plus I phi. In m you are having theta minus I phi. This is the difference between the two. Okay, so you have constructed actually two signals which transform differently under Lorentz transformation. So we are doing actually Lorentz transformation. Clear? So we are okay. So the Lorentz transformations here are affected by what? M and n. Clear? So we are having two types of matrices now, M and n, which define the Lorentz transformation on the signals. Clear? On these two types of signals. So समझ आया? तो वहाँ क्या समझ? Is it true? Is it true? Huh? Everybody is पता है कि इसको छप. Huh? So now why we started? Let's go back. Why we started? Let's recap it. Why we started? Lorentz Group. Okay? In four-dimensional space. Then what we have done? We have shown if the Lorentz Group acts on the signals, how it will do. It will be as an SU2N. So that means it gives rise to two types of signals. Is it? An irreducible representation of an SU2N, SU2. Clear? I'm simply forget about irreducible. So it gives rise to actually two SU2N. Okay, SU2 and SU2. Clear? And we have specified one SU2 with one kind of angular momentum and another SU2 with the other states in one space as one angular momentum and the states with the another, okay, with another angular momentum. Clear? And we have considered then the two special cases which actually are simply spin half particles. Okay? And we have seen under Lorentz transformation, they transforms like this way. So let's say this type of zero half, it will transform the way n acts on this signal, and here in this case m acts. So what is the take home from this construction? So you can say if I am having a spin half particle, or what a spin half means for a particle, it means it transforms as an SU2 under Lorentz transformation. Clear? So in other words, spin half particle means an SU2 particle. Clear? An SU2 particle is a spin half particle. Clear? Okay. So now we are having two matrices, two operators. Okay. So we are having these two M and N. Clear? समझ गए ना?
Yes, sir.
Okay. So what is M? So let me write first M. It's e raised power I sigma by 2 theta minus I phi, and N is equal to e raised power I sigma by 2 dot of theta plus I phi. So there is no unitary transformation that will transform M into N. Okay, so what I mean by that, let's say U is equal to unitary transformation or similarity transformation, clear, such that this U acting on M, U inverse is equal to N. So this does not exist. So what does that mean? If they are not unitarily equivalent, what does that mean? So they are distinguishable. Huh? They are two different kinds of objects. Technically we call they are inequivalent representations of the Lorentz group. Got it? So they are two different things, two different SU2s. Clear? So that means these are inequivalent under unity transformation. So these are inequivalent transformations under Lorentz group. Okay? Of Lorentz group. Clear? So okay? So that means I cannot construct any unitary operator. Look, yesterday we have seen in SU2 we have constructed actually a transformation when we are doing the transformation of the signals. So we have constructed a unitary transformation that took it to the traceless matrix. Is it? So that traceless matrix and the original matrix are the same actually. So those we call as the equivalent representation of the same object. Clear? Okay. So now, is there any other kind of transformation which makes them same? Okay. So it's actually what we call the time reversal symmetry. Okay. Time reversal symmetry. I will talk it later on, but I will do it by this way. So if you are having, okay, let me define some operation x is equal to minus I sigma y. Okay, sigma y is an operator which describes the time reversal symmetry. Clear? It's not the time traveler, it is time reversal. So there is an identity like this thing. Sigma y acting on this sigma. This means sigma x, sigma y, sigma z. You take individually. Take sigma y, sigma x, sigma y, and it gives actually you like this thing, minus sigma back. So it simply reverses the sign here. Clear? So now I can show that this m star multiplied by this x and x inverse, it gives you n. Okay? So you have to show it. So this is home assignment. So that means the signals. So let's call this as a time reversal operator for the time being. This sigma y. Okay? So that means these two signals are related by, tell me. So in this m and n, these are two transformations are two different signals. So that means they are connected by this time reversal symmetry. Okay? And it's actually an anti-unitary operation. This time reversal operator is an anti-unitary. It is not a unitary transformation. Clear? So, because we were in the moment speaking about a unitary transformation which will connect the two. This is not a unitary transformation. Samajh aaya? Clear? Okay. So we are almost done. Okay. So what is the dimensionality of this matrix? M? It's 2 by 2. Because this is a sigma is a 2 by 2 matrix. So when you expand it, it's a 2 by 2 matrix. Clear? So this n is also a 2 by 2 matrix. What is the determinant of this m? It will be 1. Exactly. The determinant of m is 1. Determinant of n is 1. So we are having now a set of matrices these for which determinant of m is equal to 1. Determinant of n is equal to 1. In other words, I can have now in general a set of matrices constructed this way. So let me take the set of matrices m. So which are actually 2 by 2 matrices for which determinant of m is equal to 1. So m, okay, so let's write this m this way. So you can construct as A, B, C, D. What are the entries here? These are complex numbers. It's a complex matrix having 4 entries. So how many parameters will be there? 8. Because these are 8 in number. But if I impose now the condition, determinant is equal to 1. AD minus BC is equal to, how many conditions are there? There are 2 conditions. Because this is real plus complex. So A plus IB is equal to 1. So real part is equal to 1 and imaginary part is equal to 0. So these are 2 conditions. Clear? So 8 minus 2, how many? 6. So that means the set of matrices, this set of matrices form a group under matrix multiplication. Clear? You can show it because we have shown it. So M and N itself are the generators of a group. Clear? Sorry, elements of the group. M and N. M is the element of group. N is the element of the group. Clear? समझ रहे हो? M specifies you the transformation. Clear? Because M is specified from what? J and K. J and K. Clear? So how many parameters are here? 6 parameters. Because Lorentz transformation is specified by 6 parameters. And you are having now a 2 by 2 group. Okay. The matrix is kind of this. So this we call as SL2C. Special Lorentz group in 2 dimensions with complex parameters. How many parameters are here? 6. So that means the Lorentz group is isomorphic to. So that is what we have shown. We have shown actually they act in the same way. So this SL2C acts where? In the Sipner space. And the Lorentz group acts in the your coordinate space. Clear? That's all. So we'll take parity tomorrow. Not in